So I think we all would agree it would be a fantastic thing if LIGO or LISA were to discover a gravitational wave background from the early universe. And that is possible. For instance, if the electroweak phase transition turns out to have been strongly first order, then it will generate gravity waves in the LISA band that could well be of detectable amplitude. However, it's not certainly it's far from a given. The next target one would really naturally think of looking at is gravity waves generated by inflation. Inflation is predicted to generate a stochastic gravitational wave background. Unfortunately, we know from constraints from the CMB background that at least for standard inflation, omega in gravity waves from inflation can't be more than around 10 to the minus 15. That's about 4 orders of magnitude too small to be seen by LISA, and about at least 6 orders of magnitude too small to be seen by LIGO, advanced LIGO. This problem, or this challenge, is what has led people to dream of what I might call a super mini LISA, which is called sort of a LISA with much more powerful lasers, bigger mirrors, 100 times smaller, which in the United States goes by the name of Big Bang Observer, or BBO, and in Japan goes by the name of DESIGO, for decihertz. In this talk, just as a shorthand, I'll continually just to say BBO instead of BBO DESIGO, but I'll really, of course, it will mean any detector of roughly the same architecture and the same noise characteristics, and whoever builds it can call it what they want. So what's the basic BBO concept? It's basically 12 satellites, 4 constellations of what you might think of as mini LISAs. These are the 12 satellites. 2 of the mini LISAs overlap to make this Jewish star. And the idea for measuring the stochastic background is to correlate the measurements from these to beat the measurements of these 2 mini LISAs against each other, much as one in LIGO looks for a stochastic background by beating L1 and H1 against each other, or H1 and H2 if you can get rid of correlated sources of noise. Each of these mini LISAs produces effectively 2 independent data streams. Aficionados here know it's really 3, but only 2 of them really have good sensitivity to both the background and to the neutron stars that I'm going to be talking about. So for practical purposes, I'm going to think of this 12 satellite constellation as producing being like 8 sort of Michelson data streams, synthetic Michelson data streams. This is a very big picture from a paper from, I think, some people probably in the room. I don't pay attention to most of it. I just wanted to show the LISA noise curve in terms of its sensitivity to omega, and the BBO noise curve. So LISA is about is about a factor of 100 up in frequency, and considerably BBO more sensitive than LISA to a gravitational wave stochastic background. It's more sensitive for 2 reasons. One, it's got just it's much more sensitive by itself. Each mini LISA is. And also, you're winning because you get to correlate 2 interferometers against each other, which you can't just with a single LISA. Why does one want to go to higher frequency, to shorter arms for BBO? Well, the point is, even if imagine if kept LISA the same size in terms of 5 million kilometer arms and increased the laser power by a factor of 100 or 1,000 or something like that, it really wouldn't buy you very much for seeing the gravitational wave background, and that's because you're faced with a big foreground. So the galactic white dwarf foreground has an omega of around 10 to the minus 11. Certainly a large part of that is isotropic. You might try to figure out what percentage of that comes from the galaxy by looking at various correlations in the shape of it, but I don't think you can beat it down by more than a factor of 10 or so. And even if you could, there's an extragalactic white dwarf background of 3 times 10 to the minus 13, which you just can't possibly get around. That's at the millihertz range. However, if you go up to above 0.2 hertz, all the white dwarfs, even the heaviest white dwarfs, have merged by then. So the white dwarf background disappears above about 0.2 hertz. Okay? Above it, there's still other, actually, white dwarf foreground. So above about 2.2 hertz, there are other foregrounds. There's a neutron star. There's basically the binaries one looks for in LIGO: neutron star, black hole, and black hole binaries. And the game to make BBO work is actually to be able to resolve every single one of those binaries and take them out of the data. So that's illustrated in this picture. So this is the BBO noise curve. It's almost 3 orders of magnitude lower in strain than the LISA noise curve. LISA is around 10 to the minus 21, a little bit. This is a little below. This is a little above 10 to the minus 24. And for comparison, I have the strain generated by primordial background of omega 10 to the minus 15, and also the background produced by all the neutron-star binaries in the universe. Okay? The thing to notice, a number of things to notice. One, notice, of course, the neutron-star, I keep saying background, neutron-star foreground is a few orders of magnitude bigger than the background from inflation you're looking for. So it all has to be subtracted out. And you have to get it down, subtract out below this level to hope to see the background. The other thing to notice is it's even above the level of the BBO noise curve. Okay? So at least when you start trying to subtract out neutron stars, the total noise curve you have to deal with is not just the instrumental noise, but the noise from all the other binaries. In this talk, so the main point at the end of the talk is to try to answer the question, can we subtract out basically every single neutron-star binary in the universe if we build a detector with this noise curve? I'm going to concentrate on the neutron-star case because that's the hardest one. So black hole neutron-star binaries and black hole binaries are more massive, have larger signal to noise, and so presumably if it's possible to subtract out the neutron-star foreground, then you can get the others as well. Okay? I think that's true. How is it possible, just briefly, to build the BBO with these parameters? Well, it involves taking LISA's laser power and upping it by a factor of 300, taking the mirrors and upping them up diameters by a factor of 12, decreasing the arm length by a factor of 100, decreasing the acceleration noise by a factor of 100. So it wouldn't be easy. So consider this a project for the future. Okay. Again, most of what I'm going to be talking about in this talk is not how BBO works or about the inflationary background that you ultimately hope to see, but really I really want to concentrate on this neutron-star foreground and try to answer the question, how well can that be subtracted out? Can you really find every single one of those neutron stars, or almost every single one, and take it out? So the next few transparencies or slides are going to be trying to give you an idea of what this foreground looks like. Okay? First thing. So what's the typical signal to noise in a matched filter sense of each neutron-star binary? So if you imagine the confusion noise has been taken away from all the foreground, and you just have the instrumental noise curve, then for a typical source, by which I mean it turns out like a source around z equals 1.5 with angle L dot n of the orientation of the binary to the line of sight of about 0.5 cosine of that angle, that sort of binary, that it will have a signal to noise of about 140. And by 140, I mean the total signal to noise taken from all 8 synthetic data streams. Whenever I say a signal to noise,
and integrated over a period of...
Integrated over the entire inspo, which you'll see is of order a year. Okay? That's right. So whenever I say SNR, I mean for the entire 8. When I show the noise curve, I mean for one of the synthetic detectors. But when I say the SNR, I actually mean for all 8. Okay, so 140, that's nice. That's the first number to make you think maybe this is doable. They're very bright. Okay? Some other things. So I often normalize things to 0.3 hertz over at the beginning of the band. So what's m over r as the binary sweeps through 0.3 hertz? It's pretty small, 5 times 10 to the minus 4 for a source at close up, higher for a source at higher redshift. That tells you that you can expect the post-Newtonian approximation to be really quite good. Whether it's absolutely good enough is an interesting question I might return to at the very end if I have time, but it's going to be at least extremely close to being good enough. If you ask how, so the time until a merger scales like f to the minus 8/3. So for a binary at low redshift, it passes 0.2 hertz about 1 year before merger. It passes 0.1 hertz about 5 years before merger. So you're thinking of the last year or so. So I'm going to try to be answering the question of, can I remove this whole background, this whole foreground? So I have to tell you what my assumptions about the foreground are, what the rate is, what the distribution what the rate has been in the past. So here are my assumptions. First, the very first, I should tell you my cosmological assumptions. A lot of these sources are at high redshift. So I'll use a rather, what I think now, a vanilla kind of universe. No one can quarrel with this too much. So H naught is 70, omega m is 0.33, omega lambda is 0.67. If the last digit there wrong, it's not going to affect anything. It's much less certain is the merger rate. So the best estimate of the merger rate for neutron-star binaries today is around 10 to the minus 7 per megaparsec cubed per year. That would be the best estimate, but it's certainly not very well known. So I'm going to also look at the range 10 to the minus 8 to 10 to the minus 6. Using 10 to the minus 7 as a fiducial value. That corresponds to a rate in our galaxy of around 1 every 100,000 years. Okay? What's it been in the past? That's the rate today. What's it been in the past? Well, so there has been a paper written about that by Schneider et al. Basically, they just take what's known and been measured about the stellar birth rate in the past, plug it into population synthesis codes, and come out with some curves showing what they think the binary merger rate has been in the past. It looks like a triangle, basically, going up to z equals 1, and then falling off again to z equals 5. And I just fit that to 2 straight lines. So in our model, the rate climbs to 3 times its present rate at z equals 1, and then drops linearly to 0 at z equals 5. That's our model.
So they're assuming that binaries typically live for times that are small compared to the age of the universe at the time they're formed.
Yeah, I guess that's right.
A short line.
So I guess the very long ones would just happen, wouldn't have had, I assume that they have some long ones in there, and then they just don't contribute to the rate currently. Okay. So given that cosmological model and that rate, and say normalized to 10 to the minus 7, how many binaries could BBO observe over, say, a 3-year observing period? And it's a lot. It's almost exactly 300,000. Okay? And this is their distribution in redshift. So about half of them are closer than redshift 1.5, but half of them are farther. So 300,000 in 3 years, or 100,000 per year. It's interesting to also answer the question, what's the distribution of sources in frequency at any instant? And that's easy to see. So you can think of all these sources that are coming in towards merger as like flowing through a big pipe, basically. And they flow fast at high frequencies and slow at low frequencies. Okay? But clearly over, say, a 3-year observation, then the total quantity of fluid or sources in the pipe is not changing, right? So then current conservation tells you that the density of sources per frequency times their df/dt has to be constant, and the constant is in fact the merger rate, how much comes out the other end, right? The f/dt for a binary goes like f to the 11/3, so the density goes like f to the minus 11/3. So you get many more at low frequencies at any instant. I'm going to digress for a minute and explain something that may have been obvious to people, but some people it's not obvious. You can ask, so we have all these binaries, we have these 300,000 binaries that BBO will observe. In what sense do they constitute a noise source? And the sense is as follows. So if you were trying to look for any neutron star signal in this whole data stream, BBO noise plus the foreground, okay, what you're going to do is you're going to, I can tell, even though the signal noise is 140, match filter sense, at any instant the signal is buried in the noise, both the foreground and the instrumental noise. So you're going to have to use match filtering to dig it out. Okay, I claim the following is true. Okay, so what's match filtering? If you have some chirping waveform H and you're looking for it in some data stream S, then you basically do this weighted integral, right? If S is constant, this is just H of t times S of t dt. You beat one against the other. You beat what you're looking for against what you got. Okay? And for a chirping signal where F is basically a monochromatic function of t, you can rewrite that this way. It's just integral of H of t, S of t dt, inversely weighted by the spectral density of the noise at F of t. Okay? So the claim is whether S of t is Gaussian noise of some spectral density, or whether it's the sum of a very, very large number of sources with the same spectral density, the result of this integral has the same distribution. Okay? That's something I prove in the paper for the particular case of chirps. But I think there must be a general argument. And there should be something you can understand on just general terms about noise. So what is noise at all times in every case, basically, ignoring quantum mechanics for a second? What noise always is, say the noise in the wire, is the result of very vast number of very completely deterministic little signals, with thermal fluctuations and things jumping back and forth, things you could have modeled if you had enough parameters in your theory. Okay? And they just all adding together in some central limit way to make some Gaussian distribution. So it's basically so many things, completely deterministic things, that you can't model them anymore. Okay? So I claim, and I showed in the paper, that you have a vast number of signals, that beating one template against those signals is basically the same as beating against noise. Okay? Yeah?
You find other here?
So that's something you choose randomly, some random thing, some random waveform. Okay. Yeah?
Just as I'm thinking about this, it seems like your sky position accuracy should be extremely good.
It is.
In any one of these.
Uh-huh.
So given the numbers that you have, it seems like you should be able to isolate them all on the sky. Just naively, like you think, to go through this process.
So I'm not claiming you can't. So yeah, you shouldn't take what I said as 100% literally. So if there were 10 to the 10 binaries, then it really would absolutely be noise, and there's nothing you could do. Okay? Instead, there's 10 to the 5, and that's good enough that you can actually take them out. But all I'm saying is that nevertheless, so eventually you'll be able to. But as a first pass, in the actual thing you're actually going to do, you're actually going to do match filtering, and you're actually going to calculate these integrals. You're going to get a big contribution from that foreground, and it's going to be as big as if there weren't that much noise in there. That's all I'm saying. Okay, I sketch a proof in the paper. I think it's quite cute, but I'm not going to go through it here. It's interesting to understand. It's important, I think, and to understand exactly why, how it happens. If you take one chirping waveform, where the correlation comes with all the others. So we have these 300,000 waveforms in the data, and I take one other. Why does it have a big overlap? Well, I claim we'll just now consider two of them. So one waveform and one other. Okay? So it's like doing, basically, forgetting the weighting for a second, doing the integral of h1 of t, h2 of d dt. Okay? And I have two chirps here, and I'm looking at the frequencies of the two chirping waveforms. And I claim that if you imagine, so this is some sinusoidal thing with a chirping frequency, and this is some other sinusoidal thing with a chirping frequency. Almost the integral is completely dominated from that instant, near that instant in time, those few hours of the year, where those frequencies are almost the same, okay, near where they cross. So there's a year-long integral. It's about 3 hours worth where all the entire contribution comes from.
Basically
Okay.
like a stationary phase.
Exactly. That's right. You can estimate from the stationary phase approximation. Yeah. So for one brief instant, it's, instead of being sine of f1t, sine of f2t, it's it's sine squared of f1t, and it integrates up. Okay. Okay. So if you ask, so that's just for 2 binaries. So this green stuff was supposed to represent the 300,000, okay? And this is the one extra track. And so the correlation of the one binary you're looking for, or think might be there, with the 300,000 others, well, it all comes from every time it passes through another frequency track. For a few hours, you get a contribution. Okay? You can ask, take one binary and ask, how often, as it's moving along through frequency space and time, does it cross another track? It's actually a rather cute answer. The answer ends up being about 1/3 the total merger rate in the universe, at all times. So it's also proved in the paper. So the total merger rate in the universe is something like 100,000 per year. So one track in a 1 year crosses about 30,000 others.
So is this true? Would this be true if you were 1,000 years from merger?
Yes, and I was about to say, it's completely independent of frequency and time. It's completely independent. And it's quite cute. You can see why it might be true. So at low frequencies, they're a gazillion, they're incredibly dense. So they're all really close together, but they're moving quite slowly. So they're not approaching each other very fast. At high frequencies, they're much less dense, but they're moving like sons of guns, okay? So they cross each other always at the same rate, right? So in 10 years, they cross 300,000 others. In 100 years, they cross 3 million others, okay? But the last year is what we're interested in.
So what are the parameters that make the speed up rate different from different binaries?
Yes, the major thing is that they exactly. So right. So if they were all, it would be quite interesting if they were. It would be a degenerate case if they were all at z equals 0 and all had the same mass, because then they'd all be parallel and they'd never cross. However, you came in, I think maybe after I showed this slide, the sources are kind of evenly distributed between z equals 0 and z equals 4 or 5. And the effective mass that determines the rate is m times 1 plus z. So the effective mass goes from 1.4 solar masses to 7. And so the rate changes by a factor of, the distribution of the rate is about factors of 2 or so. Okay? There's also presumably a small variance in the neutron star masses even as z equals 0, but it's dominated by the cosmological effect. I doubt it.
Why is it 1/3 end up with 3 end up?
So it does depend. So the actual formula is 0.5 times 5/3 times the merger rate times some factor that says the standard deviation in the effective chirp mass, which determines it over the effective chirp mass. And I calculated this for the particular distribution in redshift. So it's not always 1/3. It's 1/3 for the particular. It's always going to be of order 1 or 1/2 or 1/4, but it depends on the fact that that the masses don't vary by a factor of 10,000. They vary by a factor of order 1 or 2. It's not exactly 1/3. Okay. Okay. So what I'm trying to do is build up the pieces, go along and build up all the little pieces and facts I'll need to do the final calculation of whether you can subtract all the neutron-star binaries. So I'll need a total model for the noise. So here's the model I'm going to use. So of course there's instrumental noise. Then there's going to be a noise, basically a confusion noise, due to all the neutron stars I haven't been able to find. So all the most distant ones, basically, are the ones at whose angles are not very are more edge on than face on. Okay. So you might think that based on everything I've said that that's all there is to it. Okay. There's instrumental noise, and then there's confusion noise due to unresolved sources, and that's all I've talked about. And I claim there's an extra source though as well. And the source of that extra source is the reason for that extra source is even when you identify a binary and you take it out of the data, you never take it out perfectly. There's always an error you make. And that error leads to effectively another source of noise. I'm raising that point eventually to dismiss it and say it ends up not being very important. But it's not clear for quite a while why it isn't so important. So I'm going to talk about it for a bit. I think it's quite interesting. Okay? So far I've talked completely about noise due to binaries you haven't resolved, this huge number, say, potentially. Now I'm going to talk about, even if you resolve them, the noise, effective noise you have because you never take them out perfectly. Okay? And I claim what it effectively does is it effectively reduces the bandwidth. I'm going to claim in the end it's not a kind of noise like the others where you just add it in quadrature. These kind of errors are a different kind of noise and effectively end up basically reducing the bandwidth of the observation by a little bit. Okay? That's all I'll argue. Okay. To argue that, I'm going to need just a little bit, I'm going to assume, I think most people here know all these things, a little bit of signal processing. Okay? I didn't think I had time to review all of this. If this is unfamiliar to people, I can talk about it afterwards or something. But I'm hoping most people know that in these analysis of gravity wave signals, there's a natural inner product on the space of signals that's very useful to use. It's a noise-weighted inner product. For white noise, it's just the integral. It's just of S1t, S2t dt. And for non-white noise, it's weighted in some way. And given this natural inner product, one of the nice things about it is the signal to noise squared of any signal is just the norm squared of the signal in that inner product. And another nice feature of that inner product is if you ask, how well can I determine the parameters of any signal of the binary, let's say the binary, but of anything, say h depends on h lambda alpha, alpha equals 1 to something, 11 for binaries, then the covariance matrix for the errors is just the inverse of what's called the Fisher matrix, up to corrections of 1 over the signal to noise, where the Fisher matrix is just the inner product of dh d lambda a, the alpha, dh d lambda beta. Okay? I'm hoping that for most people here this is familiar. Based on this, you can then estimate the size of the errors you make in one line, essentially a line, 2 lines. Okay? I'm asking the question, when I take out a signal, how big an error do I make? So let h hat be the best fit, and the h be the true signal, so delta h is the difference. Okay? So the first order, it's d alpha h d lambda alpha. Okay? So now I want to look at the size of this thing.
So lambda alpha
Is the error you made in the parameters. Okay? The error you made in the parameters. So I basically want to take the norm of this, so I just square it. Okay? Right? So d lambda alpha, d lambda beta are just numbers with some expectation value. So this thing is just this thing. It's the inner product of d alpha h, d beta h, that matrix, times this matrix. But I said d alpha h, d beta h is just the Fisher matrix. And it's a famous result that the covariance matrix for the errors is the inverse of the Fisher matrix. So it's just the trace of the identity, which is the number of parameters. So that's the size, that's the norm of the error you make. Okay? So the norm of the error divided by the norm of the signal is the norm of the error divided by the signal to noise is the square root of the number of parameters over the signal to noise. Okay? So the size of the error over the size of the signal, and then for BBO, I claim there are 11 parameters, basically. And the signal to noise is typically 140. So I claim you basically make about a 2.5% error every time you pull it out. Okay? At first, that looks really bad, at first blush. because if you look back at the slide number 2 or 3 or whatever, you would have seen that the inflationary background lies at least 2.5 orders of magnitude below in amplitude the neutron-star foreground. So you want to subtract out the neutron-star background to at least 1 part in 300 or so. So at first blush, that seems like a kind of a disaster. If you thought that error just got kind of added some blind way to the data stream. But that's not what happens. Oh, before I say that's not what happens, I want to generalize it, I'm sorry. So the way I was expressing it, I was imagining it for every single binary, right? So you have 11 parameters and singularity is 140, but exactly the same argument applies to the whole distribution, all 300,000 binaries, right? Because that's just a signal with 300,000 times 11 parameters, right? And signal to noise of 140 times 300,000, times the square root of 300,000, right? And so both the error and the signal scale the same way if you think of it as a whole, the whole foreground as a signal. So the error you make in the whole foreground is also about 2.5%. Okay? Yes?
Can you remind me how you got the inflationary background?
Oh, I'm assuming it's of order 10 to the minus 15 or less. It is known to be almost scale-free for standard inflation in the regime of interest, and there's an upper limit you get from looking at the anisotropy in the microwave background, and it says you better be able to see 10 to the minus 16, 10 to the minus 17 or so. That's what I really mean. We don't really know what it is. But so we're trying to look in the region 10 to the minus 16, 10 to the minus 17. BBO should be sensitive down to 10 to the minus 17 or so. Okay, so I claim what it was true for one binary is true of the whole foreground, 2.5%. Okay, however, that 2.5% error is not like the other. It's not just an additive source of noise. The way to understand it is as follows. So think now again just of one binary. Let H. So this is let this funny surface be the manifold of waveforms. Okay, so I'm claiming it's 11-dimensional if you add up all the angles and things. So imagine this point is the real waveform we're trying that's buried in the data. But of course the data doesn't just consist of the waveform, it's that plus noise. That's this, okay? So this is what you measure. And then you do the best fit, which basically ends up being, in this norm sense, the dropping the perpendicular to the manifold. And so that's the point that's the waveform that's in the physical waveform that best fits the data is the one you get by dropping down perpendicular.
Perpendicular using your inner product.
Using the inner product. Mm-hmm. Okay. Well, what do you notice about this error? It lies tangent to the manifold of waveforms. Okay. So when you take out of the data h hat, okay, not only do you take out h, you actually take out a little piece of the noise. You take out a piece of the noise that looks like waveform. That looks like the difference between two waveforms that lies tangent to the manifold of waveforms. So the detection procedure automatically automatically interprets a bit of the noise as, so when you do your best fit, you think this is the right signal and you think that's the noise. You basically eliminated the piece of, every detection eliminates the piece of noise that lies in the manifold of waveforms. Okay? So if you actually just look at the size of the signal, that's another calculation in the paper, I'll just say it in words now. After you've done all, so imagine you could take out all the foreground sources and look at the size of what remains. You might think it's the size of the noise, it's actually somewhat smaller. Because not only have you taken out all the signals, you've taken away all the noise that lies in tangent to the manifold of waveforms. That's what the best fit procedure does. Okay? Do people understand that? Okay. That doesn't mean it's not a problem for BBO. It still is a problem, okay? Because at least in one way of doing the procedure of cross-correlating the outputs of the two interferometers, all these delta H's are still in the data, you're cross-correlating, and will look like a primordial background. So it's still a problem, but it's not maybe the naive problem you thought you had. Now let me tell you this picture tells you also how to solve the problem. So the problem is in both data sets, at least in one way of analyzing the data, where you do the best possible fit to the source, take it all out of both detector streams and cross-correlate the two interferometers in the Jewish star. You would have correlated errors due to this effect, which would mimic a big background. But the way to do that is take all the data and just throw away any data that lies tangent to the manifold of waveforms. So the idea is you have this big data set, which I claim is a vector space of about 2 times 10 to the dimension 2 billion or so from all the BBO data. And you can think of the tangent space to the manifold of waveforms as being this rather small, comparatively small space lying within the big data space. And you just project out any data that lies tangent to the manifold of waveforms. And that throws away all the errors you made, at least the first order in the errors. And then so all the errors you made in subtracting them out all lie tangent to that. I'm trying to use the fact that the errors aren't random. That's what I'm trying to say. The errors, they lie in particular very small subspace tangent to the manifold of waveforms. So you isolate that subspace, and then you throw it away. So, yes?
How well do you have to know the waveforms to do that? Because if you have an error in the waveform,
Sure.
again, you go the subtraction out the wrong, you get the wrong projection of the waveform.
Right. So in fact, about 25% of the paper, I won't have time to talk about it today, is just trying to answer that question. But so to a part in 10 to the 3 or so. And since they're post-Newtonian, quite post-Newtonian, I don't think that's undoable at all. It's a real challenge. But,
Care about the last 35.
I don't. I certainly don't care about that. But nevertheless, even so there are 10 to the 7 cycles in these waveforms. I want to get them to a part in 10 to the 3. So I want to know them accurately to a part in 10 to the 10. And the question is, does the post-Newtonian expansion allow me to predict the waveforms to a part in 10 to the 10? The whole phase. And the answer is just kind of barely.
You have to worry about resonances and then who knows what else but that?
Well, I worried about a lot of things. I didn't worry about resonances. I don't know. I'll have to think about that. So, right, that's another issue. So right now, I'm assuming you know the waveforms, and I'm just worrying about noise, right? Then there are other errors due to the fact that you might have the right waveforms. But I think those are solvable, mostly because they're so far apart in the span. Okay? Yes?
Will the subtraction operator also kill out the best fit template that you subtract there?
No, first you subtract out the template, then you hit the projection operator. You do it in that order. Okay? You can ask, when I kill that, so this is a quantum mechanical notation, this is the projection operator I would use. So how much do I throw away of the data? That's what you really want to know. Well, let me. I didn't actually put a slide in. What's this like? I think I see confused faces. So let me tell you what this is exactly like. Okay? Imagine that these sources instead were constant frequency sources, okay? And then I had lots of bins. And so let's say mostly unpopulated bins, but every like 50th bin there was a source, okay? And I took it out. But there was still some error left in that bin, right? And let's say then I was going to try to had another detector that was also had the same data and also had errors in those exact bins. All I'm doing is I throw away those bins. That's all I'm saying. Okay? That's all where all the error would be in those bins. So just throw away those bins. And this is sort of more generalized notion of throwing away those bins. Okay? Relatively speaking, how many bins are we throwing away? What fraction? Well, that's easy. Well, here's an order of magnitude estimate. I give an exact expression in the paper, but it's an exact expression that would take, I think, a few months to evaluate. Rather than evaluate it, let me just do a back of the envelope estimate. Very crude, okay? So, what's the dimension of the space of signal? What's the dimension of this big space? So there are 300,000 guys. Each of them have about 11 parameters, so roughly 3 times 10 to the 6th dimensional subspace. What's the dimension? What's the space of all the signals in it? What's all the data? Well, there are 3 years of data sampled at around 3 hertz, and there are 8 data streams. So I claim that's about 1.5 times 10 to the 9 bits, or not bits, but real numbers. So that's where you're throwing away 0.2% of the data. Okay, so it's negligible. You could ask, no one's done it yet, you could say, well, so I'll raise an objection. You can say, so you've only done actually by throwing away this tangent space, the linear piece of the error. There are also quadratic pieces. What about those? Well, you can throw those, so the cost that you can also do an extra projection operator, add another piece, and throw away the quadratic error. And that just costs you 5 times as much, turns out. So that would be 1%. So you can get away the second order errors at the cost of 1% of the data, if that turns out to be necessary or useful.
So what's some kind of Wiener filter?
What kind of fancy mean?
Maybe, I don't know. That's not the way I think about it. I think about it the way I said it before, just throwing away the corrupted bins, basically. And but if they're these fancier waveforms, the corrupted bins are possible data that changes in waveforms, that look like the differences between nearby gravitational waveforms.
This set of signals, this 11-dimensional space of signal is 90 cents complete.
I don't even know what that means. Actually, let's see. It's some curvy thing. No, I mean it's not a vector space. So that's what you mean. Not at all. So the question would be. So it's not. The tangent space is, of course, it's always flat, and that's what I need here. But the space itself, no. If you take 2 waveforms and add them, is that a waveform? No.
So what's the meaning of the gamma matrix there?
This is the Fisher matrix for the full 3 million dimensional vectors, the signal space.
So is there a way to understand easily why I'm in out directions with that kind of weighting? Or?
Well, yeah, there is. So hit this with dBH, with d gamma h. Okay? Right? So 1 minus gamma inverse alpha beta d alpha h. Excuse me.
Okay, so it's the average.
No. It's the alpha. This is just quantum mechanics. D beta h. Okay, now hit this. Now operate on this with d beta h. No, d gamma h. Excuse me. Yeah. D gamma h. Some waveform this is some waveform in the space. Okay. So this is just d gamma h.
You're really getting D gamma H delta X gamma.
Minus.
Gamma.
That's what I mean. So that's what I mean, is d lambda gamma. Okay? You're right, yeah, of course, yes. Yeah, so in one direction. Okay. Minus, so gamma inverse alpha beta d alpha h, and then this is the gamma matrix, gamma beta gamma. This is delta alpha gamma. So then this thing is again d gamma h is equal to 0. So I've shown that this projection operator kills all vectors in the vector space, tangent to the space of the manifold of waveforms. And just that. That's what it does. Okay. I will admit something. That I can say this very confidently. I haven't actually tried it with 3 million parameters. And I would like to try, I'm waiting for the day when some really brave graduate student walks in my office, and I just scared you all off, and said, yeah, I'd like a problem, because I'd like to actually try it, just to make sure it works. But I don't see why I wouldn't.
You could try with 10.
Yes, I'm pretty sure it'd work with 10. Just the 3 million scares me a little bit.
Even a cautious grad student.
Yeah, that's right. That's right. By the way, I think, I haven't tried applying these ideas to Lisa, but I was really hoping, one of the reasons that I'm doing this BBO project is I was trying to think of the techniques for dealing with, for errors and, say, extracting signals in Lisa data. So that's something I'd like to try, and that's fewer parameters somewhat. I thought of this as a warm-up problem, actually, for Lisa data now, even though it's a harder detector. Okay, so let me just summarize where we are here. So so 10 or 15 or 20 minutes ago, I raised a red herring, what I think is actually a red herring, about errors due to subtraction errors, which originally look daunting, and now I think I claim I have a method that makes them innocuous. Okay? So there might be other methods that make them innocuous. I know Sturl and Neil have a different method of making them innocuous. So any way that makes them innocuous is okay with me. Okay? So all I'm saying is from now on I'm going to ignore them. And I'm going to take the error, the total noise, to just be now the instrumental noise and the noise, the confusion noise due to unresolved sources that are very distant. Okay? Because the correction is just 0.2% due to these other kinds of errors. Okay. Again, I'm just assembling all of the pieces I need to do this final calculation in less than 10 minutes. We'll see. So one last piece I need is the detection threshold, rho theta. So how bright does a signal have to be for me to detect it? One of these neutron-star binaries. Okay? So, well, first here's a lower limit. Okay? So I estimate quite crudely that how many templates you have to use if you want independent templates to cover this entire 11-dimensional space. It's somewhere very crudely between, I think, around 10 to the 30 and 10 to the 36. It's a lot. Okay? So even if the noise is Gaussian, if you demand that the signal to noise, I'm calling rho the signal to noise, be large enough that you only have, that you don't make any errors basically in all those templates. The false alarm rate is 1%. That automatically says the rho theta has to be, the threshold has to be at least 12.5 to 13.5. And you see right away why I didn't have to make this, why this crude answer is good enough. It hardly matters whether it's 10 to the 30 or 10 to the 36 when you're way at the end of the tail. Okay? It's 13 or so, and that's just a lower estimate, a lower limit. So it's clearly going to be more than that. It can't be less. It has to be at least 12 or 13. Otherwise you get too many false alarms. Okay. But in reality, with all this huge number of templates, the detection threshold in practice will never be that low, because it's just you're too computationally difficult. So we'd like to know for an actual realistic computational strategy, what's realistic, how strong does it realistically have to be? And I don't really know. And I think it would take several months of work to even get a decent guess, to even get a really good guess. And I didn't want to do that for this problem. So, but I'll just tell you an argument that eventually gets me to the number around 20. Okay? Here's how it goes. These signals are a lot like gravity wave pulsar signals. They're an awful lot like gravity wave pulsar signals. So a binary is actually at any one moment is completely identical as a gravitational wave signal to a neutron star to a pulsar, gravity wave pulsar. So all these things are basically is pulsars that happen to be spinning down very fast. Usually you think of pulsars as spinning down at least on a 40-year time scale, and these are spinning down on a 1-year time scale. Okay? And fortunately, we've thought about in the LIGO community how to organize effective searches for gravity wave pulsars. Okay? And at least, and I in particular have done that with some grad students, and Teviot has done that. And the strategies we come up with, we have sort of complicated hierarchical strategies where you first look at a small amount of the data, say 3 weeks or so, and stack sections of 3 weeks, and get candidates, and then look more at those candidates, get a subclass of candidates, and go again, and trying to sort of match to be the most efficient as possible. And for those kinds of searches, we know what signal to noise we need to find these pulsars. Usually a factor of 2 or so above the signal to noise you need, just based on statistics alone, when you include reasonable computational power. So I looked at the two kinds of searches, and I tried to sort of find what pulsar search is comparably difficult to this neutron star search, by sort of looking at getting the size of the parameter space is about the same, and then adjusting the fact that with LIGO there's somewhat more data, and adjusting for the fact that basically it's higher frequency in the LIGO case. And to my best estimate is that the search for neutron star binaries and BBO data is about as hard as the search for unknown pulsars up to a frequency of 1 kilohertz spinning down on a time scale of as fast as 300 years. There's a hand-wavy argument in the paper that asserts that. You can ask, based on sort of computer programs we did to estimate efficiencies of neutron star searches, if you had 10 to the 17 flops at your 10 to the 17 flop computer at your disposal, and you had it free to you for an entire year, what signal noise would you need to find these guys? These kind of pulsars, and I claim the answer is 20. Okay? That's basically rerunning the pulsar code, but for really fast, slowing down pulsars. Since this argument is very rough, and so I don't completely believe it, I'm going to say maybe 20, maybe 30, maybe as much as 40. Okay? Something in that area. Okay. So factors of 2 or so above what you get from the statistical argument. Okay. Finally, I'm coming near the goal. Okay. And then I'm running behind. Is that okay? Okay, thank you. So let me again sketch out the grand strategy to how this data analysis is going to be done for the neutron stars. So presumably it works something like this. So you have all, so the neutron stars all the way up to z equals 5, and those are the least bright. But you've got some that are quite close, and you take those out first, naturally. The ones at z equals 5 have signal noise of 140. You've got some with signal noise of 300 or 400. You get those out first. Okay? But after you take them out, you've lowered the noise, the total noise. That allows you to go a little deeper. Right? Take those out, and now you've lowered the noise again. And you keep going. And the question is, if you keep doing that process, can you go all the way to z equals 5 and clean them all out? Or does it stop somewhere? And the goal of this whole research, or the biggest goal, was to try to determine in a self-consistent way whether you ever are forced to stop, whether you can go the whole distance and get them all out, and by that kind of procedure, or whether you stop somewhere, and if so, where. without actually doing it and simulating it. You could actually spend several years and actually do the whole thing and build the computer codes and simulate it, and then of course they would never get funded and you'd have wasted 10 years. And I don't want to do that. So the idea is to try to determine in a self-consistent way what the answer is without doing all that work. And the picture for the calculation I'm about to show is as follows. So you want to try to find some boundary. So roughly speaking, the signal strength of some source is basically just determined by two parameters. It's by the orientation angle mu and by the redshift z, because I'm assuming all the masses are the same. It depends a little bit on other things, but almost completely on that. So I'm going to ignore all other dependence. Okay. Then if you look in z mu space, the idea is as follows. There'll be some there'll be some line, okay, in z mu space, such that all the guys nearer than you have higher signal to noise than your threshold, okay, and all the guys below have less, and they represent noise. And the question, and you can imagine drawing this line in various places, but in fact there's only exactly one self-consistent place. Okay? So there's one, so having drawn the line, you can ask yourself, you say, I guess the line is here. Then what you do is you guess the line is there. Then you would say, okay, all these guys out here are just noise. I add them to my noise budget. I calculate the signal to noise of a guy sitting right here and find out, is it really rho theta or is it something else? Okay, I claim there's exactly one self-consistent curve. Let me try to say that again. The actual formula. Here's the method. Maybe this is a little bit easier. Okay. Okay, I fix for now some rho theta, say 20 or 30 or 40, some n naught dot, say 10 to the minus 7. I fix that for the calculation. And I make a guess of the fg squared as the fraction of the foreground that's too far away to be resolved. Okay, 10%, 1%, whatever. Okay? Then I say my total noise budget is the instrumental noise plus the unresolved binaries. Okay? Okay. With that noise budget, I can find a boundary in the mu-z plane. Okay? Such that guys right on the boundary have the detection threshold. Right? This is the formula for it. Okay? I claim. Okay. So now I have a boundary. I say, okay, now let's add up all the noise from the guys outside the boundary. And say, and compare that and get an f squared and compare that to the original fg squared. Right? So self-consistent solutions, self-consistent boundaries are fixed points of that map from initial guess to a second guess, to an iterated guess. Okay? Or equivalently, I'm looking for fixed points at f of fg, or equivalent zeros of the function f of fg minus fg. I'm looking for self-consistent solutions. Okay? That's the, okay, now finally I get to the results. Okay? So I do this for standard BBO sensitivity, and basically any of those realistic merger rates. Okay? And I do it for rho theta equals 20, 30, and 40. And BBO wins. So the only self-consistent solution for any of the realistic merger rates and say rho theta of 20 is 0. 0 left over. You get them all. There's nothing, no other self-consistent solution. And for rho f of 40, it's incredibly small, the amount that's left over. It'd be like you're saying it's basically of order one binary you miss, self-consistently. Okay. So what it's saying is like Sturl and other people who tried to get the big brother were right. I mean, they really did it pretty well. Okay. But you can say, well, it's, you'd like to see, so I had to ask the question, well, what if it doesn't work quite as well as BBO? What if it's a factor of 2 worse because, I don't know, thermal noise is a little bit worse? I say it in retrospect, that's the motivation, but really it's also just, it's embarrassing to go through all this work and just get 0 as the answer. So you want to get something on 0.
Could you have foreseen that by coming up with some kind of measure on the data space and showing that the signals were sparsely populated?
Well, no, because for the next result. So imagine it was BBO half as good. BBO with called standard over 2 BBO sensitivity, which makes so the amplitude of the noise is twice as bad, or the spectral density is 4 times as bad. Then it becomes a lot more dicey, even though the dimensions are the same. So in that case, if rho theta is 20, my best estimate actually, maybe optimistic, and there's a low merger rate, then you're okay. So this table shows the amount of energy in the unresolved mergers over this sought-for primordial background normalized to a background of 10 to the minus 15. And sort of, for the first row, you're okay. If rho theta is 20, you'd still be okay. But if it's a little harder to find these than I thought, then you'll lose, and especially you'll lose if you have a big event rate. Okay? So it's quite dicey at twice as bad. Yes, Mark?
Does it depend on your redshift distribution?
It might depend somewhat on the redshift distribution. We investigated a little, but we didn't investigate in a lot of detail. What I said, I think you might have missed it. So I used, for lack of a better, so I assumed, did you see it? It goes up. Yeah, exactly. My guess, I mean, we have it cut off at 6 instead of 5. It doesn't change anything. If there was some distribution we never thought of at z equals 10, there's a large signal, then I think that might change things. So it depends on how much you vary the redshift distribution.
So does this technique work because most of the noise is actually a low redshift? There's a luminosity function for the noise.
There is. I have a slide that shows it. But maybe I didn't put in this. I can show it to you in the paper afterwards. There is. But no, a lot of it comes from high redshift. No, quite a bit of it comes from high redshift. Okay, so if BBO were a factor of 2 worse, it would depend. And if it were, and this is just what the fractions were. This is the same information as the last curve, but expressed differently. This is the fractions of unresolved binaries. And this is the curve that gives those answers. For example, for rho theta equals 30 and these different n naught dots, this is this function f of fg minus fg, and those results are just where those curves pass through 0. Those are the self-consistent solutions. So by looking at curves like that, then you get the answer. By constructing those curves and looking for the self-consistent solutions. You can't, and this is understanding the failure of the subtraction for BBO over standard over 2 sensitivity and large rho theta. Basically, all these guys above this line would be unsubtractable, and that's just too much. If rho theta is equals 20, then just these little guys are unsubtractable, and that's okay. That may be a partial answer to your question. And then we say, what if it's 4 times worse, and then it's hopeless? So if it were BBO over 4 sensitivity, then even if my optimistic estimate was true, you could see the signal is at 20, and even if the event rate were rather low, they would completely swamp the primordial gravitational wave background, the unsubtracted guys. So BBO kind of works. So the summary then would be, we showed in a self-consistent way that, at least as best I can tell, if you manage to build BBO with that noise curve, you should be able to subtract out all 300,000 of those binaries, assuming that they have the redshift distribution that I'm assuming. If it's 4 times worse, you can forget it. And if it's 2 times worse, well, we'd have to know more about it. I also devised this projection method for handling errors, which I think might be useful. So this is my summary slide. Something I didn't have a chance to talk about, I knew I wouldn't have time, is the answer to your question, Harold. So another thing in the paper, just as the last advertisement, is that the paper is about a quarter of it is just a catalog of a whole bunch of facts, post-Newtonian effects, effects of eccentricity, lens-tearing precession, high-order post-Newtonian effects, and saying which ones are big enough that you have to include them in your model if you want to accurately capture the waveforms. So that's in the paper, but I don't have time to talk about it. And that's it. So thank you. I'm sorry I ran over.